All right, greetings everyone. This is the first part of the video on section 1.3. So we're going to start talking about something called average rate of change. Before we do that though, I do have to comment on this meme. It is one of my favorites because I just love the look on the dude's face. I think that's Tobey Maguire, but I'm not sure. But before any of you pointed out, I do want to acknowledge I'm not an English major, but I do notice that the your here is the wrong one. That should be an apostrophe RE. But it's still funny, so you can just let that slide. All right, so section 1.3, we're talking about rates of change, or we'll really be talking about average rate of change. So the official definition from our textbook, a rate of change describes how the output quantity changes in relation to the input quantity. And the units on a rate of change are output units per input units, and that's a very important piece we need to latch onto there. It's output units per input units. Okay, so again, it's telling us about how when the input changes, how does that impact the output? So some examples of this. So let's say we have a function h that describes the amount of money A that a barista will earn for working T hours. So the function is set up as h of t equals a. So notice here, the inputs are the t values, the hours. The outputs are the a, the amount of money. And it tells us here that the rate of change is $9 per hour. Okay. So first of all, we can take a rate like that, like something like $9 per hour. We can write it as a fraction. So that really is the same as $9 over 1 hour. And notice in this case, the top units, the dollars, well, those relate to the A values, the amount of money, which are the outputs. And the units in the denominator, the hours, those relate to the T values, which are the inputs, right? So we see it's output units per input units. And again, it's telling us for each change in the input, so for each change in hours, it's telling us how much the output in dollars is changing. So $9 per hour. Similarly, in the second one here, we have a function describing the number of whales after y years. And so we're given that the function is p of y equals w. So notice here the y, the years are the inputs, the w's, the whales are the outputs. And we're told that the rate of change is that the number of whales is decreasing by 8 whales per year. So in this case, our rate of change looks like 8 whales over 1 year. But in this case, it's decreasing, which tells us then it should be negative, right? So negative 8 whales per year. And again, notice the bottom units, the years, those are the input units, so the values for y, and the units on the top, the whales, those are the output units. Okay. And I also want to reiterate while we're here the notation. So p of y equaling w. So notice again, y is the input. P of y is not the input. Okay, P of y is representing what happens when we input a value for y into the function. So that's actually representing an output. So it actually represents a value of w. So in this case, P of y and w mean the same thing, but y is just the input. Okay, be clear about that because I often see students struggle with that. Okay, so let's look at an example of this. And here we have a function c of t that gives us the cost, average cost in dollars of a gallon of gasoline t years after 2000. So notice it's c of t. So the t values, which are the years after 2000, those are our inputs, and then the cost, which would be the c values, those are the outputs. So notice that's what we see here across the top. The inputs, which are the t values, and then the outputs across the bottom, which are the average cost of the gallon of gas. Also, think about what this means. When t is 2, well, it's telling us that is 2 years after 2000. So that means this 147 is representing the cost of gas in 2002, okay? Which you're probably looking at that $1.47 and thinking, holy buckets, even compared to now, I don't think we've gotten prices down that low, okay? And so what I want to look at here is the rate of change of this function over a few specific intervals, okay? So first thing I want to look at the rate of change from 2002 to 2007. Remember, a rate of change is related to change in outputs over change in inputs. So I'm comparing these values here, 2 to 147, to 7 and 264. So to find the rate of change here, the way we can do that is first of all taking differences in our outputs, because we're trying to see how the outputs are changing. So we could do 264 minus 147 over the change in the years. And I'm just going to use, even though we're going from 2002 to 2007, I'm going to use the 7 and the 2 and make sure they line up with the values they're associated with. So the 264 has to do with 2007, so that'd be 7 minus. The 147 has to do with 2002, so that would be 2. And let's also put our units on these. So these top things are dollars. These bottom ones are years. I'm just going to put Y for right now. And so then we can calculate this out. So we have 2.64 minus 147. It gives us $1.17 on the top. Over 7 years minus 2 years. That gives us 5 years. And then we can divide these numbers to get something even more accurate. We end up with 0.234, although we're dealing with money here, so I'm just going to use $0.23 per year. Okay, so notice that from 2002 to 2007, it looks like that the price of gas on average increased by about 23 cents per year. Now, notice when we look at this, if we look from year to year, so look from like 2002 to 2003, 2003, 2004, 2004 to 2005, 2005, 2006, 6 to 7, so on and so forth. Notice that the price of gas didn't actually change by exactly 23 cents each year, right? From 2002 to 2003, it went up by 22 cents. 2003 to 2004, it went up by, looks like 25 cents. From 04 to 05, it went up by 36 cents, excuse me. And then from 2005 2006, it went up by 21 cents. And then from 2006 to 2007, it looks like it went up by 13 cents. Okay, so again, this 23 cents per year is not exactly what happened from year to year. It's an average rate of change over time. All right. Okay, so what we could do, and we're not going to do right now, but normally in class what we would do is look at the rate of change over a different interval. So we did from 2002 to 2007. We could also look at from, say, 2003 to 2008 or 2004 to 2009 and compare those rates of change. And what we would find is that they're actually different over different intervals. So that's something to keep in change. Often, functions will have different average rates of change over different intervals. All right, one other thing I want to point out here before we move on, another way to write this calculation here. Well, notice that 264, that's the output we get when we input 7 into the function. So another way to write that would have been C of 7. The 147, that's what we get from inputting 2 into the function. So that represents C of 2. And this is over 7 minus 2. So notice this kind of hammers home the idea that we have a difference in outputs on the top. So the C of 2 and the C of 7 are outputs over a change in inputs on the bottom. The 7 and 2 are both inputs. All right. So kind of summarizing some of the things we talked about. So average rate of change Between two input values is the total change of the function values, the output values divided by the change in the input values. And notice that one way to calculate this is, hopefully looks pretty familiar. This y2 minus y1 over x2 minus x1. So really what we're finding here is a slope. And it's not exactly a slope, because as we kind of saw, it's kind of an estimation of a rate of change over time. But it's calculated very similar to the way that we calculate a slope. Now, I also wanted to get into the habit of using function notation in doing this. So notice here, in the second part of this slide, it says given a function f of x, the average rate of change on an interval a to b. And here a and b are input values. Okay, so from from some value a, say like 1, up to some value b, which could be like 7. So average rate of change there is, we can think of it as this f of b minus f of a over b minus a. Okay, so notice in the bottom here, you're taking the difference between those two input values. And on the top, you're not subtracting the b and the a, you're subtracting their output values when they're input into the function. All right. So as an example of that, I'm going to do the second one here. So here we're asked to find the average rate of change, back with our gas problem, over the interval from 6 to 9. And I want to be very clear that the 6 and 9, these are not coordinate points. Those are both input values. So the 6 here is corresponding to the 6 up here. 9 is corresponding to this. So to find the rate of change here, going to use that function notation version. So in here we're not going to use f's because our function is called c of t. So we see, or actually one more thing, sorry, before I do that. In this case, 6 is going to be our value for A, and 9 will be our value for B. So what we're doing here then is C of 9, since that's our B value, minus C of 6, since that's our A value, all over 9 minus 6. C of 9 from the function above is 214, minus C of 6 from up above is 251. All over 9 minus 6 is 3. If we calculate that out, I'm sorry, I'm going to do it up above. So the 214 minus 251 gave me negative 0.37. Divide that by 3. Whoops, sorry. Hold on. Calculator error here. Answer coming soon. All right, looks like we get negative 0.123 or negative 1.2. And again, this is dollars per year. So it looks like from, let's see, this would be 2006 to 2009, our average rate of change was actually negative, which makes sense, hopefully, because you notice the price of gas went down. All right, so that is calculating the average rate of change from an interval, or over an interval, using a table. All right, that's where I'm going to leave that for right now. Thank you for watching.